So today we are going to investigate our second conic section. The first one was the circle. We went through that the other day. That was certainly the simplest conic section equation that we had to deal with, fewest things going on. The complexity ratchets up a little bit with the remaining shapes, and today we're going to look at the ellipse. Now, again, there's a verbal definition for all of these shapes besides just looking at them and seeing them. And so we want to unpack what that rule is to see how the shape gets formed, and then we start to work with the equation after that. So the description of an ellipse, the verbal rule for an ellipse, is that it's the set of all points x, y. So if I take a point that's on the ellipse, like right here, or right here, any point that's on the curve of the ellipse, so that point, any of the points, if I take these two distances from these 2 points that are called foci, right? Focus is the singular, foci or foci is the plural. So I've got these 2 points that are called focus points or foci. And so if I add these 2 distances together, so call this D1 and this right here D2. If I take any other point, like if I take that point right there and I have these 2 distances, or if I take a point way over here and I add these 2 distances. So every single time I add those 2 distances together, even though they're changing, one is getting longer while the other is getting shorter, the sum of those distances is the same. So I'm going to clean up the diagram here a little bit so that we're not overwhelmed by a whole bunch of information here. But that's the idea behind the rule of an ellipse. That's what that statement up at the top is saying, is that if I take any point that's on the ellipse and I draw straight lines from these 2 focus points that are this distance c away from the center, then the sum of those distances is always going to be the same thing, the same number. And that's true for any ellipse. Now that distance will change from ellipse to an ellipse, but if I take the sum of those distances to every single point, we end up with the same number every time. Now, the equation for an ellipse, we actually have 2 different equations, but it's really the same thing as we'll see. And it has some similarities to the equation of a circle, but then it certainly has some differences. We'll try to kind of narrow those differences a little bit before we get too deep into analyzing these equations by going back to our equation of a circle. So if you recall that the equation of a circle is x minus h squared plus y minus k squared equals r squared. Well, if I take that equation and just rearrange it slightly, where I divide the entire equation by r squared. So if I divide everything by r squared, on the right-hand side, r squared divided by r squared is going to equal 1. And so we'll see that that's what we have in our ellipse equation here. We've got 1 as what our equation equals on the other side. And then the rest of the format of the equation starts to look pretty similar as well. We see the x minus h squared and the y minus k squared in the numerator in each case. Same thing over here. And then the difference is in the circle equation, I've got the same number in the denominator in both cases. Because no matter where I rotate in a circle, the distance from the center to the points that are on the circumference of the circle is the same. That's my radius. So if I have a circle, it is that perfectly spherical shape, circular shape, where this distance remains the same no matter where I go. Whereas in an ellipse, clearly we're going to have a change in what the length from the center is, but it's the sum of the distances from the 2 foci that remains constant. And so that is why we have these different denominators underneath the x and the y that we don't have in the equation of the circle. But hopefully we can see that there is some similarity here in the equations of these 2 shapes. Now, just like it was for a circle, the center is hk. The big difference here is that our denominators, a squared and b squared, are going to be different. So the rule is that whichever denominator is bigger, that is going to be our a value, our a squared denominator. And then the smaller of the two is going to be b squared. And so we can see that in the diagrams above. For the ellipse that's stretched in the horizontal direction here, we can see that a is this long distance from the center to the edge of the ellipse. And so the vertices are going to be these 2 points that are a away from the center. So that's going to be in the long direction. In the second one, a squared is shown to be in the denominator of the y equation, and that just means that we're going to be stretched in the vertical direction, so instead of in the horizontal. So just the rule is, as we see an equation for an ellipse that we identify to be that of an ellipse, whichever denominator is bigger, that's the a squared, and then the other denominator is b squared, where b is going to be that short distance across the ellipse. So we've got that defined for us here. So a is the distance from the center, and so these are the vertices of an ellipse. There are 2 vertices. There's not just one vertex, there's 2. And so a is that distance from center to vertex, and then b is just the short distance. So we call that the minor axis. So the a would be the major axis, the b would be the minor axis, and so that just flips in the orientation of the ellipse depending on whether the larger denominator is under the x or under the y. And then the other number that doesn't even show up in the equation but is essential to the shape, because that tells us where the foci are located, is this number c. So we can see that in the 2 diagrams that we have there. C is this distance from the center to these focus points that are the key part of the definition of the shape. And so the way we figure out what that c distance is by using this equation here. So it's kind of similar to the Pythagorean theorem, but it's definitely not, because it's not a squared plus b squared equals c squared. It's a squared minus b squared equals c squared. So in order to figure out where those foci are located, what that distance c is, we can't just pick it out from the equation. So if we look in the equation, we can see what h and k are, so we can find the center. We can look at find what a and b are, so we can figure out what the horizontal and vertical distances from the center we travel is. But in order to figure out what c is, in order to figure out where those foci are located, we're going to have to use this little mini equation. So if this is all a little bit kind of helter-skelter and overwhelming, have no fear. We're going to go through a couple of examples slowly here to try to break down a process for us to be able to figure out all of these relevant features and to be able to graph a couple of these ellipses.